Hello, class. Welcome to lecture 6. Today we're talking about applications of differential equations. So we're going to go through a few types. And the first kind of application we're going to look at is growth and decay. So the basic idea is that things in life change with respect to time. And so we can typically write down a differential equation describing the situation. So we're going to have a bunch of situations and we're going to describe them with differential equations. And the first situation is that we have some sort of substance or thing or amount that grows or decays. Okay, so let's see what happens here. So on some substance or thing, I'm trying to be very vague here, or maybe an amount or a population, to cover lots of different types of things. So when it's growing or decaying, we can model this with a differential equation because growing or decaying means that it's changing with respect to time. And so we can bring in a derivative to describe that. Okay, so there are lots of ways for things to grow or decay, but we're going to cover just one for right now. And what we're going to do is we're going to name some variables to make things easier to write down the differential equation. So we're going to call n the amount or the population or whatever you want to call it. But it's really the amount after some time. So it's dependent on time. And I guess I should say that time we'll call little t. And so n is really, in the differential equation, you'll write n, but it's really a function of time. So you should really know that it's the same as that. Okay, so then if it's the thing that's changing with respect to time, then what is that? That's the derivative. So dn dt is the rate at which this amount changes. And it's either going to grow, so there's going to become more and more of this thing, or it's going to decay, there's going to be less and less. So it's the rate at which this amount changes over time. Okay, so these are the little variables we need. And then what we need is a description of what's going on that we can take and write a differential equation from. So one way an amount can change over time, or sorry, one way an amount can change is proportionally, hard to spell, proportionally to the current amount. So hopefully that's a believable fact. The more you have right now, the more it'll grow, or it'll continue growing like that based on how much you currently have. So then what does this mean? Well, proportionally just means that they're the same up to a constant multiple. So this means, well, if it's changing this way, that means that the derivative, the rate at which it changes, is equal to, and if it's proportional to the current amount, that means it equals the current amount, but not exactly, but times some constant, which people call like a constant of proportionality or something. If you want to use fancy language, you don't really have to call it anything. It's just there. Proportionality, which I probably spelled incorrectly. Okay, but in any case, this is the differential equation describing the situation. And this is just a differential equation that we know how to solve. So this models growth and decay. proportional to the current amount. And again, there are other ways to model growth and decay where things grow or decay differently, but this is just one. This is the first and easiest way. Okay. And we can solve this. So let's solve this. It's separable. So all I have to do is to get the ends on one side. The constant is just a constant. I can leave it wherever I want, but I'll put it there. And it's separable, so I can just integrate both sides. And then I have this, and then I want my function of time, my amount to be alone, so that I have a formula that tells me the amount after time t. So I will solve for n. And so you can leave it like that, but you can also think of it as, well, it's a function of time. And then I can rename this constant, like I always do, to be just c in the front. And so we get this. So this is the function that tells us the amount after time t when you're in this situation. So notice I've solved the differential equation before any details have been added. So I don't really know what k is. It's just some constant. And c always appears when I solve a separable differential equation like this. And in the specific situation, these two pieces of information will be filled out. So then I will get a specific function like 5e to the 2t or something, which describes the growth of a specific situation and solves a specific differential equation instead of in general. Sorry, I have to pause because my house is very loud really quick. Okay, so then this might look a little bit familiar to you. So you may have seen, whoops, I guess I accidentally switched to red without thinking about it. May have seen something like A equals PE to the RT or something in pre-calc, PERT. And this is where it comes from. It's really the same equation, except in pre-calc, you don't know where it comes from. You just use it to model like how much money grows over time or something. But it's in that situation, your money is growing proportionally to how much you currently have. And that's why you're using the same formula. Okay, but now we know where it comes from and we're going to use it for other stuff. So here is the first word problem example. And it's going to take me a while to write it down. So I'll pause it and then I'll pop it in real quick. Okay, so here is the word problem. Bacteria culture is known to grow at a rate proportional to the amount present. So we are in the correct situation where our differential equation describes the situation. But now we also have these two other facts. After 1 hour, there will be 1,000 strands, and after 4 hours, there will be 3,000 strands. So what these really correspond to are just additional conditions. So we've done initial value problems, and it sort of works the same way as those problems did. And then this last part is just telling us what we want to actually do, which is we want to find n of t, because we're trying to find an expression for the number of strands. And in this problem, n of t is the amount of bacteria. Okay, so let's actually solve it. So it's good to just say what everything is. So you don't have to say what time is because it's always little t, but you should say that n of t is what in this situation? Well, it looks like we're talking about numbers of strands. So I'm going to call n of t the number of strands of the bacteria. So I don't know much biology, but I guess that's how you can measure bacteria after time t. And that's really the only thing, because the others are just based on that. So dn dt is just the rate at which the number of strands grows. So a rate at which, you don't have to write this part down. I'll just write it. Strands grows. And because it's known that the growth is proportional to the amount, I can say this differential equation describes this situation. So it's the same differential equation as before, so it still is solved the same way. So I don't really have to show it every single time. I will keep it as n of t though, because just to remind us that it's a function of time. Okay, so this solves the differential equation, but it doesn't solve the problem because this doesn't tell me how many strands there are at time 50 or whatever I want to plug in, because I don't know C and K. So that's where this extra information comes in. So it's not always given to you in the same way, but here's one way it can be given to you. So what is this really saying? Well, this first sentence is just saying that if I wait 1 hour, there'll be 1,000 strands, but that really means that if I plug in 1, I should get 1,000 as my amount. So you can think about this as an initial value problem, which is saying to solve this differential equation subject to n of 1 equals 1,000. And that just means that, well, I've already solved it. So now I say that at time 1, meaning plug in 1 for t, it'll equal 1,000. So then I get this little equation, which doesn't let me solve for C or K, but it helps me a little bit once I use the other condition too. So now I'm also adding in this other condition from the other sentence. So after 4 hours, there's 3,000 strands. That really just means plug in 4, get 3,000. And all of these problems will be very similar, except they will give you different conditions in different ways to help you find K and C. This is just one possibility. This is sort of the most annoying way because I have to now solve a system of 2 equations with 2 variables. But it can be done. Okay, so let's do it, I guess. I guess I can solve this one for C. And then I can plug that in there. And then I can figure out K by doing that. So we get 3 equals e to the 3k. Once I simplify, ln both sides. And I finally figure out k is ln of 3 over 3. And then if I put that back in here, I get that c is a 1,000 over e to this number, which you can simplify if you're comfortable with logs, then go ahead and do that. But I'll just leave it so I don't scare anybody too much. So then to actually answer the question, so what is the function that describes the amount after time t? Well, it's this same function, but now I know what my 2 constants are. I know what c is, and I also know what k is. So now if I plug in a time and just calculate it out, I can always figure out the amount after time t. Okay. And that's about it. Other problems, though, they will ask you other things to do and give you different information, but it sort of always amounts to the same thing. Okay, so one thing you should just note real quick is that for growth and decay problems, it's always the same differential equation. So you're always going to get this thing. And it's not exactly a 2-parameter family of solutions, even though there's 2 constants. It feels like it, but it's still 1 parameter, and I'll tell you why. It's because this k here, it doesn't give you a whole bunch of solutions to the same differential equation, because this k also changes they're the same k. So if k equals 5, for example, you're not solving tons of differential equations with that k. You're just solving the one differential equation where this is also 5 because they're the same. Whereas c is a parameter because as c changes, you're getting tons of solutions to the same differential equation. It doesn't matter what k is, any c will still solve it. So just keep that in mind. It's not technically a 2-parameter family. It sort of feels like it is, and we need extra conditions to figure out both constants, but it's not technically a 2-parameter family of solutions. Okay, so let's do another example just to see how this works. I will pause again, copy paste. Okay, so here is the next problem. This time we're talking about the population of a country. So it still counts as an amount. And in this country, the amount is increasing. So it's changing at a rate proportional to the current population, the number of people alive there. So this is saying that we are in the same situation. And then we're given these extra conditions that are a bit different than last time. So now what we know is after 2 years, the population doubled instead of some specific amount. After 3 years, we do know a specific amount, 20,000. And then we want to find the initial population. Okay, so once again, we can write down some things. So what's n in this case? It's just the population. After some time, we have the same differential equation with the same solution. Now what we need to do is figure out k and c with our conditions. So after 2 years, the population doubled. What does that mean? Well, let's see. After 2 years, the population doubled. What can I say about that? Well, that means after I plug in 2, something should happen. The population should double. What does that mean? Well, it's kind of hard to see unless you know what the original population was, aka the initial population. So first, let's think about what that means. The initial population means what did the population start at? So when time was just beginning at 0, that's what initial population means. So at 0 time, I'm trying to figure out what that is. That's the actual question. And I can do something with that already, actually, because 0 is so nice to plug in. I can get that n of 0 is just c. So really what I'm looking for when I say find the initial population is I'm trying to find c. And then what I could say is, oh, double the initial population, that would just be 2 times c. So now I know what this condition is telling me. This is telling me if after 2 years the population doubled, that means that when I plug in 2, the answer should be 2 times the initial, which is 2 times c. Even though I don't know what c is, I can still write this down. This is a condition. And then the other condition I have is that after 3 years, the population is 20,000. So that one's a bit more straightforward. Plug in 3, get 20,000. Okay, so I'm going to apply these 2 conditions to our differential equation and see what happens. So if I plug in 2, I should get 2c. And what does that let me do? Well, that's interesting because that actually lets me solve for k immediately because I can divide out the c's. So whenever you have a condition like doubling or tripling or something like that, it's going to let you do this type of thing where the c's cancel. Okay, so then I can just ln and get k. Great. So I have k, but I really want c. So let's see if this other condition helps me do that. So if I plug in 3, I should get 20,000. Well, now I know k is this, so I can also use that there. And I'm plugging in 3 for time. And yeah, now I can solve for c if I just divide this over. And you could simplify this if you want. That's the answer. So the point is that this problem is not asking you for the function, although we could now plug C back in to actually finish getting the function that corresponds to the population after time t. But different questions will ask you for different things. Okay, so that's it for that one. Lots of other types of different things, but they all amount to giving you conditions in different ways and solving for different things. Okay, but we're going to move on to a new application, enough growth and decay. So this is called the falling body problem. You may have studied something like this in a physics class. And in physics, what we do is, in basic physics, at least when I took it, is you suppose an object is falling, and maybe you draw a little diagram like this. The dot is the object, and you draw a little arrow going down. And what do you need to know about the object? It has some mass, which you call m, and what we're trying to figure out is we're trying to determine the velocity, how fast it's falling, which you call v, but it's actually going to depend on time. As you fall further, it changes. As time is passing, it changes. And of course, time is t. And what do we want to do? We want to determine velocity. Well, what we're going to do is we're going to describe the velocity in a differential equation, and then we'll be able to solve for it. Okay, and in a physics class, what you do is you usually ignore air resistance if it's a basic physics class because you're not ready to handle it. But here, now that we have differential equations, we don't need to ignore air resistance. So we'll actually get to have a more truthful expression for the velocity than you saw in those classes. Okay, so to describe it though, we need some laws or rules to help us write down differential equations, just like with the growth and decay we did, need it again. So here is one law. The total force, which more people call it the net force, but I like the word total force. It's like all the force on the object. We're going to call that capital F. And the law about capital F is that F equals the mass times the derivative of the velocity. So how fast the velocity is changing. This is more commonly known as acceleration. So how fast your speed changes is your acceleration. But velocity also accounts for direction and not just speed. Okay, so how fast your velocity changes is acceleration. If I multiply that by the mass, I get the total amount of force on the object. The other law we need about the total force, well, it equals, because it's the total force, it's all the force, the sum of all the forces on the object. So what we need to do is we need to think about what forces are at play on this object. So if I have an object falling down, what forces are pushing on it? Well, there's gravity, which pushes it down. And I'm going to name that force at capital F and a subscript grav. And gravity, the force of gravity is just equal to the mass times the gravitational acceleration constant, which is 9.8 or something. Meters per second squared. I'm not going to worry so much about units because I'm not a physicist, but it's just a constant. Mass is another constant, so this is really just a constant here. Okay. So that is pushing the object down. So maybe let me redraw it like this. So here's the object. You can think about gravity as pushing it down, but there's another force pushing it up, which is air resistance. Air resistance is pushing back up. It doesn't like stop it, so you're falling harder than it's pushing you up, but it's there. And I'm going to call that force F sub air. And the idea is that it is proportional to how fast you fall. So the faster you fall, the more air resistance will push back up against you. So it's proportional. That's the key word, which means it's a constant, and it's proportional to what? To how fast you're going. So times your velocity. But then what we like to do is we like to realize like, oh, they're pushing in opposite directions. So if one of them is positive, then the other should be negative. It doesn't matter which one you decide as long as you stay consistent. So gravity, I'm going to count as positive. So going down is positive and going up is negative. So I'm going to say that there should be a negative there because they're in opposite directions. Okay, so then the amount that the gravity pushes you down plus the amount that air resistance pushes you up, according to this law, should equal the total force. And this gives us the differential equation. So then total force equals gravity pushing you up plus air resistance pushing you down. Now we plug everything in. Gravity is m times g. Air resistance is negative k times the velocity. And the total force is m times the derivative of the velocity. So this gives us our differential equation, which we can rewrite and see that it's linear. And now we know how to solve linear equations. So let's see, I'll add kv over divide by m, and then I'll get this. Okay, so this is linear. So we can then use a technique to solve it. Integrating factors, e to the integral of k over m dt, and this will be e to the k over mt. That's my integrating factor. By now we're experts at integrating factors, so we multiply it to both sides. And then on the left, it always becomes the derivative, or sorry, no, just v. So I'm going to multiply it to this thing. Becomes v times the integrating factor, because v is like our y variable right now. It's the thing changing with respect to time. Now on the right, you multiply it, and then we have the integral. So then integrating this, we get m times m over k times g, if you do u sub, e to the k over m t plus the constant. And now I can solve for my velocity function. And I get, so if I divide by this, I get, I'm going to write it as gm over k. This thing will cancel with that when I divide it. And then over here, it'll be underneath, so it'll have a negative power. And I'll get that. So this tells me the velocity at any time t for a falling object in the presence of air resistance. And you should always sort of try to think about these things to like see if they match your intuition. So when something is falling and there's air resistance, the object should eventually reach something called terminal velocity, where you're going so fast that the air resistance is pushing you back up enough to keep you from speeding up further. And so does this formula tell us that there's a terminal velocity? It does, because as time goes on towards infinity, this thing here, well, it has a negative exponent power. This is going to go towards zero because you're getting C over a big number that just gets bigger and bigger. So it's going to go towards 0. So then the velocity is just going to approach this other number, gm over k, which is a constant. And this is the terminal velocity here. So this is what should happen in air resistance, and when there is air resistance, and it does happen. So it's good to know. So we're not going to do as much as we did with the growth and decay in terms of plugging in initial values and solving for C and K. Just a lot harder than it is for those ones. But in general, what's going on is G and M are constants that you're just preemptively given, so you don't have to do anything for those. C and K, you figure out with some sort of initial conditions if you want, but it's actually a lot harder. Okay, so that's it for today. I'll see you next time.